Okay, so here's a problem. We want to determine the maximum positive moment at point C, and we have a single concentrated live load, a uniform live load, and a dead load, which is the weight of the beam. So I'm going to show you how to handle those forces, how they're applied. But first we need to find the moment at C. So remember in Mueller-Breslau, we can find the qualitative shape by doing what? We're going to assume that C has no moment capacity, which is basically a hinge. Right? And we're going to come back, and as the principle states, we're going to apply the thing we're looking for. So since we're looking for positive moment, we'll apply that. So here's some moments. Now with that kind of force applied, this hinge, do you think it's going to move up or move down? Yeah, I think it's probably going to move up. And as it does that, the hinge will allow rotation. It's still anchored at A. It's still anchored at B. And it kind of seesaws over that to the free end. So we have now the qualitative shape of our influence line. So I'll go ahead and redraw it. So I now know the moment at C, my influence line, as a function of x, looks like this thing I've just drawn. It peaks at 4 feet. I just did not draw this to scale, but I think you'll get the idea. And I'll just go ahead and write underneath it, this is 4 feet, 4 feet, and 4 feet. I did a better job drawing it up here than I did here, but the idea will be okay. So now what I have to do is I need to figure out what the value, the ordinate of this graph is, either at this point or this point, and then use similar triangles to find the other one. So remember, we're trying to find the moment at C for a unit load varying over the length of the beam. So I think this might be the easiest position to deal with, when the unit load is at 4 feet. So what would that look like? That would look like a beam still has a pin at A, a roller over here at B, but now I'm looking for the unit load right there. So that's the position. This value on the influence line really relates to our unit load being at this position. Now what am I looking for? I'm looking for the internal moment at C. So I'm going to have to cut it right there too and find this internal moment. So thinking about that into the future, into our next step, if I were to actually cut it here, which side of the structure do you want to work with? The left side or the right side? I don't see really any overwhelming advantage, but just because I like to work from left to right, I'll say I'll work this side. So if I do that, I need to know my reaction at A. So how do I find my reaction at A? Yeah, you can sum moments about B. So we'll do that. So if I sum my moments about B, make sure I'm in equilibrium, my unit load is creating positive moment with the moment arm of 4. AY is creating negative moment with the moment arm of 8. So I think when you solve for this, you'll see that the result is not surprising. It's 1/2. You probably suspected that already because the load is right in the middle of this section and the reactions are sharing it equally. So now what I'm going to do is I'm going to cut the structure at C, which is 4 feet away, and internally I'm going to find the moment at C. And also I know that my reaction AY is 1/2. Now whether you include or not include the unit load, I'll put it in there. You can see it has really no moment arm, so it's not going to affect the moment either way. From that position, I'll sum the moments at the cut. And what do I have? Well, my internal moment MC is positive with my sign convention. AY is going to create negative moment, which will be 1/2 times 4 feet. So it looks like the moment at C for this position is just 2. So that means that this value is 2. And also the units for the moment are in length, which in this case will be feet. So if this is 2, what's this value? -2, right? 2 is to 4, so there's the similar triangle as this one unknown is to 4, so they're equal, -2. So now I have my entire influence line. So that wasn't too bad. Again, if I had to do this the previous way, I would have had at least 2 sets of equations to write. So this is a little bit faster. Yes?
So I understand it's not shear moment diagrams, but conceptually does the area under an influence line represent anything that we would use?
We're going to use it next to estimate the force.
Okay.
So now that I have the influence line, so this shows me how a moving concentrated load affects the moment at C. So the question is what's the maximum positive moment that can be developed by this set of loads? So let's first start with the concentrated live. So that is a concentrated force. Live means it moves around, of 8 kips. Well, remember we built our influence line for a dimensionless value of 1. So superposition allows us to take all these values and multiply them by 8 to get this result. Now, where is the largest positive ordinate on this graph? +2. Remember, I'm trying to find the maximum positive moment. If I wanted the maximum negative moment, where would I go? All the way out here at 12 feet. So right now that says that the position of our live concentrated load to create the maximum moment at C would be here at 4 feet. So what is that value? So our concentrated live load, meaning it moves, would be what? It would be 8 kips times this ordinate, which is 2 feet. So that tells me that the moment produced there will be 16 kip feet. So that's the position or the contribution to the maximum moment at C due to the live. All right, let's do this one next. Let's do the dead load. Does it move? That means the dead load extends, because it's the weight of the beam, it extends the entire length of the beam. You have no control over how to apply the dead load. The dead load is just everywhere. Now remember, we talked before about if you have a uniform distributed load, how do you calculate its effect? I think this gets back to Mr. Warburg's question, is like, what do we do with this thing? Does the area under the curve make any difference? Yes, it does. You remember that the way you figure out the influence is you take the area under the curve times the value. So now that if I want to do the dead load, I'm going to have the load, which is 1 kip per foot, and I'm going to multiply it times the area, total area of this curve. In this case, they're all triangles, so I'll put my 1/2 on the outside. So everything's going to be 1/2 base times height. So the first one is going to have a base of 8 feet times a height of 2 feet. This triangle will have a base of 4 feet times a height of minus 2 feet. Everybody see that? So this part here is simply just the area under this curve.
Which curve?
The influence line. So the unit load, or the intensity of the unit load, times the area of the curve. I don't know what that is. Let's see. So this is 16 minus 8 is 8. Half is 4. Times 1 is it 4? So that should be 4 kip feet positive. So I've got 16 from the concentrated load, an additional 4 from the dead load. So far, so good? Now this is the one that we have to do a little thinking about. So the next one is a live uniform load. Now live loads move around. Even though this is uniformly applied, as an engineer, you kind of get to decide, where do I put my live uniform load to create the most effect? In this case, the most positive effect on the moment. That's a pretty irritating noise, isn't it? Are your teeth vibrating in your head? Mine are. I need to get some WD-40 for that card. Who is that? Oh, yeah. This is not recorded, by the way, so don't worry about it. Okay, so where do I put it? Do I put it over here?
0 and 8.
Well, if I put it over here, sure, it'll contribute, but it'll make a negative contribution. So I'm just going to put it between the first 4 feet and the next 4 feet. So now when I look at that contribution, you can see that value is 3 kips per foot. So I'll have 3 kips per foot. Again, it's a triangular load, so I'll just pull my 1/2 out. And I'm just looking at the positive part. So that'd be 8 feet for the base of the triangle, 2 feet for the height. And so this contribution is just going to be, what is that, 24 kip feet? 8 times 3? So I'll just add all these together. So the moment at C, positive, max, is just going to be these added together. So that's 20 plus 24 is 44. So that's the maximum moment that I can generate at C for this set of load. Now, what does that structure look like? So let me just come down here real quick and make a sketch of what the structure looks like. And the first thing I'll do is I'll put on the dead load. This is the weight that is across the whole structure. Right? So that's the dead load, the 1 kip per foot, right? The whole structure. Where does the uniform live load go? Just over the first 8 feet, right? So that would look something like this. And then where does my concentrated force go? I think we found it to be right here, which is 4 feet over, which is about right here. So this would be where my 8 kip force would be. This is where my 3 kip per foot force is, and then my dead load over here, which is 1 kip per foot. So this loading configuration generates that positive moment at C.
And that's 44 just because you added up some of those?
I added up all the components. Everything is linear, so we can just superimpose the effects.
Okay.
So that is typically the problem you will get, like on an exam or on homework from now on, because it combines not only the drawing the influence line, but then using it with the various loading components we have to generate a maximum value.
But you said if we could do that because it's linear, what case would you have where it's not?
Well, all of our structures are linear, so there would not be a case you would encounter in this course that would you wouldn't have to worry about it.
So the live uniform load is just over the first 8 feet is positive?
Right. If we wanted to do the maximum... Sorry, yes, Mr. Chris?
So this is just the maximum moment at that point.
At C.
So there could be a higher moment in the beam somewhere.
Yes.
Why would we want to look at just the maximum positive moment? Because then you always say that for the most part, the sign is going to matter when you design you want.
Well, it's a simpler problem. If I asked you what just the maximum moment would be, you'd have to do both positive and negative and tell me both. So we could do that, and I think you could look very quickly and say, well, what if we did the negative? Well, if you do the negative, the dead load doesn't change. So you're going to get a positive contribution from the dead load, period. Okay, where will we move our concentrated load? From this position to this position, right? So this would generate negative 16. We still have positive 4, right? What about the uniform live load? Where would we do that to create the maximum negative effect? It would just be the last 4 feet. And you can see that's half the area of this one. So you'd get half the value. This would be negative 12. So you get negative 16 plus negative 12 is 28, right? And then 4, you get negative 24, which is much smaller than positive 44. So in that particular case, or in this particular case, the positive moment is the more controlling of the two. And you can really see that too by the diagram. The diagram shows you more positive area than negative area. So that's your tip-off of how it's going to affect it. So any other questions about? We're going to work some more problems. Any more questions about this one?